Well, microservice architecture enables large teams to build scalable applications that composed of many loosely coupled services. Well, here is a typical microservice architecture looks like. For example, consider this is a microservice architecture for a simple shopping cart application. It has different services like product service, inventory service, stock service, and these are the independent and loosely coupled services. In microservices project, each microservice have their own database. For example, product service has their own database, inventory service has their own database, and stock service has their own database. And in microservices project, all the microservices are loosely coupled. So loosely coupled meaning all the services in a microservices project are independent to each other, and each microservice should be developed independently, and each microservice should be deployed independently, and each microservice should be scaled independently. Okay, so basically each service will have their own database, each microservice should be developed independently, each microservice should be deployed independently, and each microservice should be scaled independently. In microservices project, services can communicate with each other. For example, product service can communicate with inventory service, and inventory service can communicate with stock service, and product service can communicate with multiple services as well. For example, product service can communicate with inventory service as well as stock service. Well, there are two types of communication styles. One is synchronous and another is asynchronous. In case of synchronous, we can use HTTP protocol to make a HTTP request from one microservice to another microservice, and in case of asynchronous communication, we have to use a message broker for asynchronous communication between multiple microservices. For example, we can use RabbitMQ or Apache Kafka as a message broker to make a asynchronous communication between multiple microservices. And each microservice in a microservices project can expose a REST APIs. For example, product service can expose the REST APIs, inventory service can expose the REST APIs, and stock service can expose the REST APIs. And here product service can communicate with inventory service. It means product service have to call the REST API of inventory service using HTTP protocol. Each microservice can expose the REST APIs, and each microservice can call another microservice's REST APIs using HTTP protocol. So this is the synchronous communication. And in case of asynchronous communication, the microservices have to use a third-party component or a message broker for asynchronous communication. Now let's take a look into the key components in a microservices architecture. Well, the key component is API gateway. Well, whenever a client sends a request to API gateway, and then API gateway will route that request to the relevant microservices. Alright, and here the client can be a web application, a mobile application, or a desktop application. Alright, and whenever a client want to consume the REST API's backend services, the client have to first send a request to API gateway, and then API gateway will route that request to the relevant microservice. And here one more key component is a service registry. Well, all the microservices in our microservice project will register to service registry, and the API gateway will discover the particular microservice hostname and port using service registry, so that API gateway can route that request to particular microservice. And one more key component is config server. So this config server component will basically externalize the configurations of microservices. And one more key component is distributed tracing. Well, in order to maintain the logs or complete log hierarchy of a particular HTTP call, we can use distributed tracing. Alright, so these are the few key components in a microservices architecture. So just remember, microservice architecture enables large teams to build scalable applications that composed of loosely coupled services, and each microservice have their own database, and each microservice expose the REST APIs, and each microservice is loosely coupled, and each microservice developed independently, each microservice deployed independently, and each microservice scaled independently. So these are the important characteristics of each microservice. Alright, so this is all about microservices. Well, Spring Cloud is essentially an implementation of various design patterns to be followed while building cloud native applications. Instead of reinventing the wheel, we can simply take the advantages of various Spring Cloud modules and focus on our main business problem than worrying about infrastructure concerns. Well, these days, many organizations prefer to deploy their applications in a cloud environment instead of taking all the headache of maintaining data center themselves. But we need to take good care of various aspects to make sure our microservice applications are cloud native. So there comes the beauty of Spring Cloud. Alright, so Spring Cloud basically an implementation of various common design patterns that we can follow to build cloud native microservices applications. Well, if you go to official website of Spring Cloud over here, Spring Cloud provides tools for developers to quickly build some of the common patterns in a distributed systems. For example, configuration management, service discovery, circuit breakers, routing, API gateway, distributed sessions, cluster state, etc. etc. Alright, so Spring Cloud provides a lot of common patterns that we can use in our microservices project to solve different problems. For example, look at here, Spring Cloud provides these different models to implement different common design patterns in our microservices project. For example, we can use Spring Cloud config module to implement Spring Cloud config server pattern so that we can externalize the configuration of our microservice applications in a central repository. Next, Spring Cloud provides Spring Cloud Gateway module to implement API Gateway pattern in a microservices project. Well, API Gateway basically sits between client and backend microservices. And whenever client sends a request to backend microservices, the client request first comes to the API Gateway, and then API Gateway, based on the routing rules, it will forward that request to the appropriate microservice. Okay, so API Gateway pattern is very important whenever we develop the microservices project. Next, Spring Cloud provides Spring Cloud circuit breaker module to implement circuit breaker pattern in a microservices project. Well, in microservice-based architecture, one service might depend on another service, and if one service goes down, then failures may cascade to other services as well. So Spring Cloud provides Spring Cloud circuit breaker module to handle this kind of issues. Next, Spring Cloud provides Spring Cloud OpenFain module, which we can use as a declarative REST client to make a HTTP call from one service to another service. Okay. Next, Spring Cloud provides Spring Cloud Sleuth module, which we can use to implement distributed tracing in a microservices project. Next, we can use Spring Cloud Netflix module to implement service registry and discovery pattern. Well, in microservices project, we may have hundreds of thousands of microservices, and in order to scale our microservices project, we will start multiple instances of required microservices, isn't it? And let's say if multiple microservices are down in our project, then we need a mechanism where we can keep track of which microservices are down and which microservices are up. So in order to solve this kind of issue, we can use service registry, isn't it? The main advantage of service registry and discovery pattern is that we can avoid hard coding the host names and ports. For example, let's say microservice A is calling to microservice B, then microservice A don't have to hard code the host name and port of microservice B. Alright, we just have to register microservice A and microservice B to the service registry, and whenever microservice A want to call microservice B, then microservice A just have to use the load balancing URL provided by service registry. Microservice A don't have to hard code the host name and port of microservice B. Okay, so these are the few important Spring Cloud modules. So just remember, Spring Cloud provides tools for developers to quickly build some of the common patterns in a distributed systems. So distributed systems here nothing but a microservices project, and we can use different Spring Cloud modules to implement different common patterns in a distributed systems. Well, we are going to use employee management project as an example to create a microservices architecture. Well, you can take any example of any project. For example, you can take e-commerce application, or you can take any healthcare domain related application. So you can take any project as an example, but follow the same steps to create a microservice architecture using Spring Boot and Spring Cloud. Well, we are going to create three core backend microservices: employee service, department service, and organization service. And all these three microservices have their own databases Well, we are going to use MySQL database as a database for these microservices. Okay, so whenever you create a microservice in your project, make sure that each microservice should have their own database. Alright, once we build the microservices, next we will see how these microservices communicate with each other. Well, we are going to use different ways to make a REST API call from one microservice to another microservice. For example, we will use a REST template, we will use web client, we will use Spring Cloud provided OpenPaint library. Well, once we know how microservices communicate with each other, next we are going to implement service registry and discovery pattern in our microservices project. Well, Spring Cloud provides Spring Cloud Netflix Eureka based service registry model that we can use to implement service registry and discovery pattern in our microservices project. Well, service registry and discovery is very essential pattern that we can use to avoid hard coding, hostname and ports. Next, we will implement config server to externalize the configurations of all these three microservices into a central place, that is Git repository. Well, Spring Cloud provides Spring Cloud config module that we can use to implement config server to externalize the configuration files of all these three microservices into a central place. We are going to use Git repository as a storage for config server. Well, once we know how to use config server to externalize the configuration files, next we are going to implement API gateway. Well, the API gateway plays a very important role in a microservices architecture. Okay, so whenever a client want to make a call to different microservices, then client have to remember the host name and ports of all these microservices. So there should be a solution where a client can send a request to the central component. So that is where the API gateway comes into picture. So whenever a client sends a request to the backend microservices, then client have to send a request to the API gateway post, and then API gateway, based on the routing rules, it will route that request to appropriate microservice. Okay, so this is how the API gateway plays an important role in a microservices architecture. Well, Spring Cloud provides Spring Cloud Gateway model to implement API gateway pattern in a microservices architecture. Next, once we know how to implement API gateway in a microservices project, next we are going to implement a distributed tracing in a microservices architecture. Well, Spring Cloud provides Spring Cloud Sleuth module, which we can use to implement a distributed tracing in our microservices project. Well, along with Spring Cloud Sleuth, we will also use Zipkin to visualize the tracing log information in a user interface. Well, Zipkin provides a user interface to track the trace information through web application. Okay, so once we know how to implement distributed tracing using Spring Cloud Sleuth, next we are going to create a simple React application which will make a REST API call to backend microservices. Well, we are going to implement circuit breaker pattern in an employee service because employee service is internally calling department service, and let's say due to some reason department service is down, then employee service won't get a response from the department service, isn't it? And then again employee service will send internal server error to the API gateway, and then API gateway will send that response back to the client. Alright, so in order to avoid this kind of issue, we can use circuit breaker pattern. So this circuit breaker pattern helps employee service to avoid a continuous calls to the department service whenever department service is down, and this circuit breaker pattern will help employee service to return some default response back to the API gateway, and the API gateway will send that default response to the client. Alright, so this is the simple microservices architecture that we are going to follow to create a microservices project using Spring Boot and Spring Cloud. Consider in our microservices project we have multiple microservices. For example, microservice 1, microservice 2, and then microservice 3, and so on. Okay, and each microservice have a host name and port. For example, let's say microservice 1 is running on port 8080, microservice 2 is running on port 8081, and microservice 3 is running on 8083. And in order to scale our microservices project, we can run multiple instances of each microservices, right? For example, let's say if we want to scale microservice 1, then we can start another instance of microservice 1. For example, let's say the instance is running on port 8084, and another instance will run on a port 8085. Okay, and each microservice exposes the REST APIs. Alright, next here we have a client. It consumes a REST APIs from multiple microservices. For example, let's say client consume the REST APIs from microservice 1, microservice 2 and microservice 3. Well, in order to consume the REST APIs from microservice 1, microservice 2, microservice 3, client have to know the URL of all the REST APIs. Well, in enterprise application, we may have hundreds and thousands of microservices, and it is not a good idea that client have to interact with all those, microservices, isn't it? So basically, client have to remember all the host and ports of all the microservices that it want to consume. So in order to solve this problem, we can use API gateway. Well, API gateway basically sit at the middle of client and backend microservices, and whenever client want to consume the REST APIs from multiple microservices, then client have to first send a request to the API gateway. It don't have to interact with directly to the multiple microservices. Okay, so this is awesome, right? So client don't have to remember host and ports of all the microservices that it want to consume. It just have to send a request to API gateway. That's it. API gateway take care of routing that request to appropriate microservice. Okay, so this is how the API gateway solves the problem. Okay, client don't have to tightly coupled with multiple microservices. Client just have to send a request to API gateway. API gateway based on the rules or the URL rules, it will forward that request to appropriate microservice. So API gateway we basically use to route the request, and second is we can also use API gateway for load balancing. For example, let's say we want to scale microservice 1, then we'll start multiple instances of microservice 1, and then API gateway will take care of routing the request to particular instance. Okay, in this way API gateway also capable to handle the load balancing. Next, security. Consider we are not using API gateway, then what will happen? Each and every microservice have to implement its own security, and client have to authenticate with each and every microservice, isn't it? So this is basically a tedious process. Alright, so client have to authenticate with each and every microservice it want to communicate. So this is a tedious process, isn't it? So API gateway basically address this problem. We just have to implement centralized security in a API gateway. Client just have to authenticate with API gateway. That's it. Client don't have to authenticate with each and every microservice it want to communicate. And API gateway will take care of authenticating the client request, and if there is any issue, then API gateway will send a response back to the client. Alright, so API gateway will address this security cross-cutting concern as well. Now let's take a look into the slides. API gateway provides unified interface for a set of microservices so that clients no need to know about all the details of microservices internals. It means that API gateway will hide all the microservice internals. Okay, so client only have to send a request to API gateway, and API gateway will take care of routing that request to appropriate microservice. Next, API gateway centralize cross-cutting concerns like security, monitoring, rate limiting, etc. Well, we can implement a centralized security in a API gateway. We don't have to implement a security in each and every microservices. Okay, and whenever client sends a request to API gateway for authentication, then API gateway will take care of authenticating the request, and if there are any issues, then API gateway will send a response back to the client. Okay, in this way we can implement centralized cross-cutting concern like security. Now the question is how to implement API gateway in our Spring Boot microservices project. Well, Spring Cloud provides Spring Cloud Gateway to create a API gateway. For example, if you look at the architecture over here, we can implement API gateway in our Spring Boot microservices project using Spring Cloud Gateway library. Well, if you go to browser and just search for Spring Cloud Gateway and go to the official documentation, you can go ahead and read all about Spring Cloud Gateway over here. Well, Spring Cloud Gateway is a part of Spring Cloud framework, and Spring Cloud Gateway provides a library for building API gateway on top of Spring Webflux. Alright, if you want to know more about Spring Cloud Gateway, then you can go ahead and check out the official documentation. In microservices projects, service registry and discovery plays an important role because we most likely run multiple instances of services and we need a mechanism to call other services without hard coding their host names or port numbers. For example, in typical microservices project, we have a lot of microservices. Consider we have 3 microservices in our microservices project, and in order to scale our microservices project, typically we start multiple instances. For example, let's say I want to scale microservice 1, then what I will do, I will start multiple instances of microservice 1. For example, let's say instance 1, instance 2, and so on. And consider microservice 1 is running on port 8080 and microservice 2 is running on port 8081 and microservice 3 is running on port 8083. And whenever we start another instance of microservice 1, then this instance port should be unique. Let's say this instance is running on port 9091 and this instance 2 is running on port 9092. Next, let's say we want to scale microservice 2. Then what we'll do, we'll start multiple instances of microservice 2. For example, let's say microservice 2 instance 1 and then microservice 2 instance 2 and so on. Right. Next, let's say microservice 1 want to communicate with microservice 2. Then microservice 1 have to know the host name and port of microservice 2 as well as its instances. Okay. And again, let's say if microservice 1 want to communicate with microservice 4, then microservice 1 have to know the hostname and port of microservice 4. If you can notice here, microservice 1 have to know the hostname and port of each and every microservice that it want to communicate, isn't it? And let's say if we want to start another service of microservice 2, then we need to also configure that instance hostname and port in a microservice 1. Okay, so this is the pain basically, isn't it? We as a developer, we need to configure a lot of stuff. Okay, and there should be a mechanism where we need to only configure the microservice 2 ID so that microservice 1 can directly talk into microservice 2. Microservice 1 don't want to talk with the other instances. Okay, that is where the service registry comes into picture. If we use service registry, then microservice 1 don't have to bother about the hostname and port of all the microservices and instances that it want to communicate. So microservice 1 have to only know about the microservice 2 application name or the ID. That's it. Service registry will take care of configuring the appropriate request. In microservices project, service registry and discovery plays an important role because we most likely run a multiple instance of services and we need a mechanism to call other services without hard coding their host names and port numbers. So this is what the point we have discussed over here, right? So if we use service registry, then we don't have to bother about the host name and ports of the microservices and its services. All right, let's take a look into the second point. In addition to that, in cloud environments, service instances may come up and go down anytime. So we need some automatic service registration and discovery mechanism. Well, in typical microservices project, we may have a lot of microservices and its instances running, right? And we need to keep track of all the microservices and its instances at a single place. That is where the service registry and discovery comes into picture. So basically in our microservices project, we need to register all the microservices to service registry, and service registry will track all the microservices and its instances, and we can use service registry to see what are the microservices are up and what are the microservices are down. Okay, in this way we can use service registry and discovery to keep track of all the microservices and its instances in our microservices project. Now the question is how to create a service registry and discovery in our Spring Boot microservices project. Well, Spring Cloud provides Spring Cloud Netflix Eureka project to create a service registry and discovery. Well, let's first understand what is a problem and what problem Spring Cloud Config Server solves. Consider in our microservices project, we have multiple microservices. For example, let's say a microservice 1 and then microservice 2 and then microservice 3 and so on. Okay, and in order to scale our microservice project, we basically start multiple instances of each microservice. For example, let's say we want to scale microservice 1, then we will start the multiple instances of microservice 1. For example, let's say instance 1 and instance 2 and so on. Okay, and each microservice has a configuration files. It contains the microservice level configurations. For example, let's say microservice 1 has the configuration file, and similarly microservice 2 has a configuration file, microservice 3 has a configuration file. And consider we have a requirement to update the configuration file of microservice 1. Then what we need to do is we need to restart microservice 1 as well as its instances. Alright, so this is not a good idea. Each and every time whenever we update the configuration file, we need to restart the microservice as well as its instances. This is the problem Spring Cloud Config Server addresses. If we use Spring Cloud Config Server, then we no need to restart the microservice and its instances whenever we change its configuration file. Okay, so first problem, restart. Okay, so if we use Spring Cloud Config Server, then we no need to restart the microservice and its instances whenever we change the configuration file. So this is the problem the Spring Cloud Config Server solves. Next, we can use Spring Cloud Config Server to externalize the configuration files of each and every microservices. Right now, each and every microservice has a configuration file in its project itself, right? So we can use Spring Cloud Config Server to externalize all the configuration files of all the microservices in a central repository or a central place. For example, let's say Git repository. Alright, so if we place all the configuration files of all the microservices in a central repository, then we no need to go into each and every microservice to change that configuration file, right? So whenever there is a requirement to change a project specific configuration file, then we can simply change in a Git repository so that it will get reflected in that particular microservice. We don't need to dig into that microservices and change that configuration file. Alright, so this is the problem also Spring Cloud Config Server addresses. So these are the two major advantages of Spring Cloud Config Server. First one is whenever we change the configuration file of that microservice, then we no need to restart that microservice as well as its instances. Second advantage is like we can externalize all the configuration files of all the microservices in a central place, so that whenever we have a requirement to change a project specific file, then we can simply go ahead and change in that central place. We no need to go into that particular microservice and change the configuration file. We can simply change at a central place. Okay, so these are the main advantages that Spring Cloud Config Server provides. Alright, great. Well, let's first understand what is the problem and what problem the distributed tracing solves. Well, one of the challenge in microservice architecture is the ability to debug the issues. When there are a lot of microservices in our microservice project, then the user request will span many of them, and it will be difficult to trace the logs for a particular request where an issue occurs. Well, one simple end user request might trigger a chain of microservice calls, and there should be a mechanism to trace the related call chains. For example, consider in our microservices project we have multiple microservices. For example, let's say we have microservice 1, and then we have microservice 2, and then we have microservice 3, and then we have microservice 4, and so on. Okay, and here let's say we have a client, and whenever a client make a request to microservice 1, microservice 1 may internally call microservice 2, and microservice 2 may internally call microservice 3, and microservice 3 may internally call microservice 4. So this is how the chain of microservices calls goes. Okay, let's say due to some reason there is an issue occur while this chain of microservices calls, then it is very difficult to debug the issue. I mean, it is very difficult to identify where exactly the issue occur, isn't it? Because there are a lot of microservices talking to each other, isn't it? So there should be a mechanism to keep track of this complete request flow from start to end. This is where the distributed tracing pattern comes into picture. Okay, so if we use distributed tracing pattern, then we can trace the complete request from start to end. This is awesome, right? We can use distributed tracing to trace the chain of microservices calls from start to end. Okay, and also we might want to track down why certain microservice call is taking too much time. This is where also we can use a distributed tracing to identify which microservice is taking how much time. All right, so basically distributed tracing solves this kind of issues. Well, event-driven architecture is a software design pattern in which decoupled applications can asynchronously publish and subscribe to events via event broker or message broker. Well, in a event-driven architecture, the decoupled applications will basically use a message broker or event broker for asynchronous communication between publisher and subscriber. Alright, in an event-driven architecture, applications communicate with each other by sending or receiving events or message. Well, in event-driven architecture, the event means an action. Okay, so whenever something happens inside or outside your organization, an event has occurred. So events basically means actions that can be anything. For example, if you consider this event-driven microservice architecture over here, this architecture has three applications or three microservices: order service, stock service, and email service. And whenever a customer places the order, then that time the event will be created. For example, create event, and that event will be published to message broker. And then stock service and email service, these two services will basically consume that message from the message broker. And in this event driven microservice architecture, all the applications are loosely coupled. Okay, so they are independent to each other. Alright, so event driven architecture means it is a software design pattern in which all the decoupled applications will use message broker for asynchronous communication. Okay, so this is how the event driven architecture looks like. Well, event driven architecture is often referred as a asynchronous communication. For example, if you consider this event driven microservice architecture over here, this architecture has multiple microservices, right? Order service, stock, and email service. Well, order service, whenever it will create the order event and it will push that order event in a message broker, then order service don't have to wait for the response. It can proceed to executing its other remaining task. Okay, so this is how the asynchronous communication. Whenever a order service, it will create the event and publish that event to the message broker, then it don't have to wait for the response. Okay, so this is the asynchronous communication. Well, event-driven applications can be created in any programming language because event-driven is a programming approach, not a language. Well, you can develop event-driven architecture in any programming language. Well, an event-driven architecture is loosely coupled. For example, consider our architecture here, event-driven microservice architecture. In this architecture, we have three microservices: order service, stock service, and email service. And all these three microservices are independent each other. It means all these three microservices are loosely coupled. Okay, so order service, you don't have to know about stock service or email service. Order service just have to send an message or event to the message broker. That's it. You don't have to know about the consumers. Alright, similarly, stock service and email service, so these are the consumers and they don't have to know about the producer. They only responsible to consume or read the message from the message broker. They don't have to know about the producer, okay, who is producing the messages. Alright, so this is how the event driven architecture looks like. So in an event driven architecture, all the applications are loosely coupled. Alright, so this is all about event driven architecture, and event driven architecture is widely used in microservices. We'll take a look into how event driven microservice architecture works. Well, in an event driven microservice architecture, we create multiple microservices and we use a message broker as a messaging system for asynchronous communication between multiple microservices. For example, we have order service as a microservice 1, stock service as a microservice 2, email service as a microservice 3. To keep it simple, let's consider we have 3 microservices, but you can create as many microservices that you want. For example, you can create SMS service, you can create payment service, you can create packaging service. Okay, so in order to understand event driven microservice architecture, let's consider we have these 3 microservices in this architecture. In event driven microservice architecture, we have to use a message broker for asynchronous communication between multiple microservices. A message broker can be a RabbitMQ or Apache Kafka or Apache ActiveMQ. Okay, so you can use any message broker that you want for the asynchronous communication between multiple microservices. So whenever a customer places an order, the order service will basically create an order event and it will publish that order event to the message broker. And stock service and email service, so these are the basically consumers who subscribe to this message broker. So as soon as order service publishes order event to the message broker, then these two microservices will receive that order event. Okay, and stock service basically responsible to receive the order event from the message broker and it will update that order details in the database. And email service, it is responsible to receive an order event from the message broker and it will send email to the customer about this order status. Well, you might be wondering what are the advantages of using event-driven architecture. Well, the first advantage is it improves the flexibility as well as maintainability. Well, maintainability plays a very important role whenever we develop the application. Well, in this architecture you can see order service is only responsible for collecting the order and creating order event, and it will place that order event in the message broker. And similarly, stock service is only responsible for updating the stock in a database, and email service is only responsible to sending the email to the customer. So all these three microservices have their own purpose and they are independent to each other, right? So order service don't have to know about stock service and email service. Okay, so these are the basically independent. So there is a lot of separation of concerns between these three microservices. That's why in an event-driven microservice architecture, the publisher don't have to know about the consumers. Okay, and consumers don't have to know about the publisher. They just use middle component, that is message broker, for the communication. Okay, so this is the separation of concern and it improves basically flexibility and maintainability. Let's say you have a requirement to create one more microservice in the architecture. Then what you need to do is you need to create one more microservice similar to stock service and email service, and then you need to start consuming the events from the message broker. You don't have to worry about the publisher, isn't it? So this is called basically scalability. In event-driven microservices architecture, it provides the flexibility to scale your microservice architecture. You can create as many as microservices that you want. Alright, so this is a very important feature of this architecture. Well, one more advantage of this event-driven architecture is that it improves the availability. For example, consider we have multiple microservices in the architecture and any one microservice goes down, then it won't affect the other microservices because all the microservices are independent each other, right? If any one microservice goes down, then it should not impact other microservices. Okay, so but if you use a monolithic approach, then there is a lot of issues, like if any functionality goes if any functionality fails, then it may affect other functionalities as well in the monolithic applications. But in event-driven microservice architecture, all the functionality or all the microservices are independent each other. That's why if any microservice goes down, then it won't affect other microservices. Okay, so this is the one of the big advantage of using event-driven architecture, and all the microservices are loosely coupled. Alright, so these are the few advantages of using event-driven microservices architecture. We'll understand what problem circuit breaker pattern addresses. Well, consider in our microservices project, we have multiple microservices. For example, microservice 1, microservice 2, microservice 3, microservice 4, so on and so forth. And consider microservice 1 is calling microservice 2, microservice 2 is calling microservice 3, microservice 3 is calling microservice 4, and so on and so forth. Okay, so in typical microservices project, we may have hundreds and thousands of microservices, and microservices are dependent on each other, isn't it? And if we can notice here, whenever a client make a request to microservice 1, for example, let's say client, then microservice 1 internally make a call to microservice 2, microservice 2 internally call microservice 3, and microservice 3 internally called microservice 4. So this is basically a chain of microservices calls, isn't it? And consider if due to some reason the microservice 4 is down, and if you can notice here, microservice 3 is dependent on microservice 4. So if microservice 4 is down, then microservice 3 it won't work properly, so it may down. And if you can notice here, microservice 4 is dependent on microservice 3, and if microservice 3 is down, then microservice 2 won't work properly, or it will also goes down. Okay, and notice here, if microservice 2 is down or won't work properly, then microservice 1 also won't work properly, because microservice 1 is dependent on microservice 2. Well, notice here the impact of entire microservices calls chain over here. If microservice 4 goes down, then it will impact other microservices as well. This is the one use case when microservice 4 goes down. Consider if microservice 4 is slow due to some performance issue, then it will impact microservice 3 as well, because microservice 3 is dependent on microservice 4, right? And if microservice 3 get a response slowly from microservice 4, then it will again impact to microservice 2, because microservice 2 is dependent on microservice 3. Similarly, it will impact on microservice 1 as well, because these microservices are dependent on each other. Well, we can see this kind of issues in a microservices project. Now we may have a question like, can we implement a fallback method mechanism? For example, microservice 3 is dependent on microservice 4, right? So in microservice 3, we can implement a fallback method mechanism. Fallback method mechanism meaning whenever a microservice 4 goes down, then microservice 3 will return some default response to the microservice 2, and then microservice 1 will get that response from microservice 2. Okay, in this way we can avoid cascade failures. Alright, so next is like, can we implement a circuit breaker pattern? Circuit breaker pattern. Well, circuit breaker pattern, what it does basically, whenever microservice 4 goes down, then it won't allow microservice 3 to hit the request to microservice 4 continuously. Okay, so if we implement circuit breaker pattern, then we can save a lot of resources, and we can avoid a continuous calls from microservice 3 to microservice 4. Next question is, can we implement a retry mechanism? Well, in case of retry mechanism, consider if my microservice 4 is temporarily down, then we can implement a retry mechanism in microservice 3, so that microservice 3 will retry multiple times calling microservice 4. For example, let's say if we configure retry as 5, then microservice 3 will retry sending request to microservice 4 5 times. So basically microservice 3 will retry multiple times, and if microservice 4 is up, then it will get the success response from microservice 4. So in this way we can implement a retry mechanism in microservice 3. Alright, next question is, can we implement the rate limiter? So basically rate limiter pattern will limit the number of calls from microservice 3 to microservice 4. Alright, so these are the questions basically provides a solution for this kind of impacting entire microservices calls chain issues.